So our next gig is a tiny little bar in North Lansing this coming weekend, so pretty low-key. So I decided to talk about supermassive black holes, and I wanted to make a direct connection to you. It's a bit of a long chain of reasoning, so that's why I invited you to sit down for it. So, the connection between supermassive black holes and you starts with talking about what the ingredients for life are. And life needs elements. They need like carbon, oxygen, iron. So I have a couple of pictures from Frankenstein, various movies from Frankenstein here. You have elements. Also needs energy. Dr. Frankenstein knew that to animate his monster, he needed to infuse it with energy, so life needs elements and energy. So, the first event in the universe, and yeah, it is kind of a long story, so we have to start at the beginning. The first event in the universe was the Big Bang, and about 5 minutes after the Big Bang, the periodic table had begun to be assembled, but it was still pretty small. It only has the elements of hydrogen and helium and trace amounts of lithium, beryllium, and boron. And that's not enough for life. We need more complex atoms to have life. So we really owe the Big Bang a lot. After all, it gave us space and time and matter and energy, so that's good.
So I got that going for me, which is nice.
So you can't really hear him, but Bill Murray says, "So I got that going for me," which is nice. He was talking about, let's see, what was it? Total consciousness, which is also nice. The sun, which is good, provides us energy today, okay? But the sun doesn't provide us the elements that we need. The sun was born at the same time that the earth was. And so whatever the sun has and the earth has, all those elements were generated before the sun was even a thing. So the sun is about 5 billion years ago. So the elements that make up the earth and the sun and everything had to be made before 5 billion years. So, billions of years ago, many generations of stars died to make you some oxygen. And I'm going to play a little video. This is from NASA. We're zooming into the core of a red supergiant star, so we're going way down into the core where the nuclear furnace is. That's assembling the elements from hydrogen and helium and making the more massive elements like carbon, oxygen, and eventually iron. Iron's sort of a dead end when it comes to nuclear fusion. You can't get any more energy from that, so stars that start to build a core of iron eventually explode, and that redistributes those elements back into the rest of the universe in the supernova explosion. It leaves behind a black hole or a neutron star. Some of those black holes then merge. That's what's going to make you some gold. So this is an animation that was created by the European Space Agency to show what happens during the merger of a neutron star. What you're seeing there, illustrated by the artist, is the gravitational waves that are sent out by that event, gravitational waves that have been detected by the LIGO observatory most recently, and then the afterglow captured by astronomers called the kilonova. And this kilonova event has evidence that the heavier elements in the periodic table are created in this neutron star universe. So maybe maybe that will be Nobel Prize #2 for LIGO. The first Nobel Prize went to that team and others for the discovery of gravitational waves from 2 merging black holes, which has no electromagnetic signature. So stars and their remnants, like neutron stars, detonating white dwarfs, make most of the elements heavier than hydrogen and helium. Those are the elements necessary for life. And this is a depiction of the periodic table, and it's color-coded. The elements on the top, the lightest elements, hydrogen and helium, are created mostly in the Big Bang. Stars make some of the helium, but not much of it. The elements coded in blue are made by supernova of various types, either massive stars blowing up or white dwarfs that blow up after merging or exceeding the mass that they can support themselves. The orange is coded because late-stage red giant and red supergiant stars also assemble heavier elements. In fact, most of the carbon in your bodies were probably made in the late stages of red giant stars, called carbon stars. The yellow is coded to indicate the elements that are likely created in neutron star mergers. And a lot of this color coding happened in the last, I would say, few years or so. Before that time, we were suspicious that maybe neutron star mergers could create these heavy elements. But I think with the direct detection of a neutron star merger plus the afterglow, it really is seeming like it's a more certain declaration. But anyway, so we should be thankful to stars for making those elements. All right. Oops. So multiple generations of stars, mostly long dead, billions of years ago, long dead, made the elements that are inside you right now today. But you needed more than just stars floating out there in space to make elements. You needed a galaxy. And you need a galaxy because galaxies are places where stars form. It takes a galaxy of stars to make enough elements so you can get rocky planets and people. The universe is full of galaxies, about 100 billion galaxies in the observable universe, each with about 100 billion stars. This is a picture taken with the Hubble Space Telescope of the Andromeda galaxy, so I can zoom in. These galaxies are full of stars. Each major galaxy has about 100 billion stars in it. So galaxies provide the environment that you need for these repeat generations of star formation. So over on the right-hand part of this slide, I'm looping through a movie of showing you how tiny fluctuations in density grow to make larger densities. Whoops, that should have worked. Whoop. Okay, so over there, so again on the right, what you're seeing is tiny fluctuations of density where there's overdensities. The overdensities get bigger with time. The underdensities also get bigger, so the difference between the two grow. It's sort of like the rich get richer, the poor get poorer, and you know, like a nasty economic system. It just happens. But gravity works like that, naturally enhances small density fluctuations and makes them bigger density fluctuations. Galaxies are where most of the matter will collect. They're the sites of the highest matter densities in the universe. When stars form, when they blow up, winds blow, that tends to push gas away. So if the stars were just isolated, floating out there in space, you'd have one generation of stars, it would push the gas away, and there'd be no more elements forming. So for life to really happen, you need to have a concentration of stars forming one generation after another to build up the heavy element abundances that is necessary to make rocks. You need rocks to have surfaces. You need surfaces to collect water. You need water for chemistry. you need chemistry for life. So these repeat cycles of star formation and star death are necessary, and you're only going to get that in a galaxy. So, galaxies don't just hold together on the basis of stars alone. You need gravity, and you need matter, and you need a lot of it. And you have probably, some of you have been coming to these talks for a while, may know that the universe has a mass energy budget, and much of it is matter, but most of it is this stuff called dark energy that Professor Everard mentioned in my introduction. Galaxies themselves don't have a lot of dark energy inside them. Dark energy likes big empty spaces. It's related to the size of things. Some people think it's got something to do with the vacuum energy of the universe. So the more vacuum there is, the more dark energy there is. So galaxies really internally are not affected much by dark energy. The universe sure is. But galaxies are where matter is concentrated. So the universe mass energy budget isn't the same as the galaxy's mass energy budget. The galaxy's mass energy budget is mostly mass. So we're going to look at this part of the wedge where it's dark matter, gas, and stars, and then just look at that budget. So you have mostly dark matter, about 85% dark matter, 15% gas, and only 2% stars. So that's why I was saying stars aren't enough to hold the galaxies together. You need a lot more matter. Gas alone also isn't sufficient. You need a lot of dark matter. Now, there's an audit alert in this chart. In a typical galaxy, we only know about where 10% of the gas is, and we don't know exactly what dark matter is made out of. All we know is that it's not made out of the usual stuff like protons and neutrons and electrons, that the rest of matter is accounted for. So there's a whole, another talk that we could give about the search for dark matter and what it's made out of. What we do know, though, is how much there is, and that's why we can make a chart like this. Gravity has a way of affecting the orbits of stars and so forth, and we can tell how much matter there is from studying that. So, dark matter holds the galaxies together. So a little gratitude for the dark side. Okay? All right. So things to be grateful for. We're approaching Thanksgiving, so we can be grateful for a lot of things. We can be grateful for the Big Bang. We can be grateful for the stars that form the elements. We can be grateful for the galaxies as birthplaces of multiple generations of stars. We can be grateful to our sun for giving us free energy. So you came to this talk, though. It's like, what's our connection to supermassive black holes, right? So here we go. In the center of every galaxy, apparently, there is a supermassive black hole. Now, the supermassive black hole doesn't hold the galaxy together, but I'm going to explain why that supermassive black hole is important to galaxies and our story about how galaxies evolve and make stars. So, in our own galaxy, this is a picture of the Milky Way, an all-sky picture. No one telescope can capture this picture unless you can see both the north hemisphere and the southern hemisphere. So this is made from a compilation of pictures. And I'm going to zoom into the center using, this is all real data, and I'm going to acknowledge Mark Voigt, my husband, for assembling this series. This was all very, very precisely aligned and put together. So what you're seeing is a zoom in. Now you see the little rectangle in the center. We're going to zoom into that rectangle now. Okay, we're still seeing more, but now as we get close to the center of the Milky Way, we need infrared light to really peer through the dust and gas that sit between us and the center of the Milky Way. So I'm going to start showing a scale bar here. So that's 250 light years. A light year is a distance that light takes to travel in 1 year. It's about 10 trillion kilometers. This is the radio view of that same area. And we're going to zoom in into this rectangle. And we're seeing a lot of, the red is the hydrogen gas that's towards the center. The bright little spot on the right-hand side that's labeled Sagittarius A, that's where the center is. We have the scale bar on the left, again, showing where 50 light years is. And this is the radio image superimposed on that. Okay, now we're going to zoom in on that box over Sagittarius A. Okay. Sagittarius A has a lot higher star density than our local neighborhood. I would imagine that the night sky around, if you were in a planet around one of these stars, your night sky would be pretty well contaminated by light. You wouldn't be worrying about Starlink. There's 5 light, so that's 5 light years. So for a little bit of scale, our nearest star to us is 4 light years. So this neighborhood's pretty packed. Okay, this is the radio, bit of the radio image. All right, we're zooming in again, closer to the center. 1 light year. Okay, so we are starting to zero in. Okay, so this is very, very close to the center. This is a map of the locations of stars separated by periods of 1 year as they move around a very dark object. So each of these orbits is orbiting a central object using Kepler's laws, which you might be familiar from your Astro 101 course, that says that every object is an ellipse, every orbit is an ellipse, and the focus of one of the focus points is the point of the central position. So each of these ellipses has a common focus, and it's right there in the center, and all of these stars are orbiting. So we can tell from these orbits what the mass is in the center. And let's see. All right. Come on. Here we go. So hopefully this works. I may have to click one more time. All right. So these are observations taken with interferometric techniques by Andrea Ghez and her group at UCLA. And hopefully it will circle around. There we go. Okay, so did you see that one that was very, almost came in radially and then took a left turn and is back out up to the right? That very precisely locates the dark object that's being orbited here. And that dark object is an object that has 4 million solar masses. And it's clearly not glowing. So this is some of our best evidence that the dark object in the center of our Milky Way is a 4 million solar mass object, supermassive black hole. And this is a picture of Andrea Ghez. And if you are on the Nobel Prize Committee, she's a good candidate. I would vote for her, okay? Just in case. I don't know if there's any Nobel Prize Committee candidates in the audience, but that's my plug. So very recently, you probably remember last spring that there was an announcement from the Event Horizon Telescope of the discovery of a picture. They made a picture of the event horizon of the black hole in M87, M87 is 1,000 times farther away, but it's also about 1,000 times, the black hole is about 1,000 times more massive. So the event horizon in M87 is about the same size on the sky as the event horizon for the center of the Milky Way. So I would predict that, barring any technical difficulties, that the black hole in the center of our own galaxy will be the next released target from the Event Horizon Telescope. But the first one was M87, and for some, because of reasons of transparency to M87 versus to the center of our galaxy, it was actually the easier target. And this is a visualization, a zoom into M87 that was quickly assembled by Frank Summers of Space Telescope Science Institute to celebrate this discovery. And he put some music to it. So the supermassive black hole in the center of M87 is a little more active than the one in the center of our own galaxy, so it has this radio jet that is kicking out of it. The Event Horizon Telescope is also a radio telescope, so a lot of these images that you are seeing are taken in radio, at the radio wavelengths. So we're zooming into the jet. The jet has a base for the red, over there in the left-hand corner. Parsec is about 3 light years. So all of these pictures that you see going forward were taken with arrays of telescopes spread across the planet to act like a big telescope. So this is the celebrated image. There's the size of Neptune's orbit if it were circling around M87's black hole. So, Twitter said this picture was blurry. Screw Twitter, man. This is a simulated picture that was prepared for the movie Interstellar. They knew what it was going to look like. They had help. Kip Thorne, another Nobel Prize winner, helped with this particular movie. So how was that accomplished? That was accomplished with radio telescopes located on different parts of the world, thousands of miles apart. And when the signal is combined, it can act like a telescope that's much, much bigger than any individual telescope in the network. So it's almost like having a planet-sized radio telescope looking at the center of the Virgo cluster, the center of its most massive galaxy, and directly imaging the event horizon. That's the region from which light cannot escape around M87. So people have been studying these things for a very long time and estimating their masses in various ways. Clearly, imaging the event horizon is the very toughest way to go, but there's other ways of measuring their masses by measuring how fast gas circles around the galaxy center, or measuring how fast stars are moving around the galaxy center. And so people have assembled estimates for masses of the central black holes, and what all those measurements have been assembled into charts. This is just an example of one of those charts. On the vertical axis is the mass of the black hole as estimated by one of these mass estimate methods, and on the horizontal axis is what we call a velocity dispersion of a galaxy, and that tracks with the mass of the galaxy itself. And what you can see is that there's a correlation between the mass of the galaxy and the mass of the black hole. And that's circumstantial evidence that the galaxy and the black hole somehow know about each other. Even though the black hole is a tiny percentage of the total mass of the galaxy, and even though the black hole is, you saw those zoom-ins, it's a very, very tiny piece of the galaxy that the black hole actually influences gravitationally, yet somehow the black hole and the galaxy, when it's big, when the galaxy is big, the black hole is big, and when the galaxies are small, the black hole is small. And how that happens is not particularly obvious. But you remember, those pictures of M87 showed this jet. And here's an artist's conception of a black hole that's erupting as matter swirls around the black hole and eventually falls into the black hole. Some of that matter is ejected out in these jets. This matter has to lose large amounts of angular momentum to actually settle into the black hole, and jets are a way to take some of that angular momentum and get rid of it. So jets seem to be a fairly common feature of accretion disks around almost anything. Even protostars have jets forming, and these supermassive black holes have really, really big jets. So this is a picture of a galaxy. The center fuzzy thing, that's a massive galaxy, one of the biggest galaxies in the local universe. And the pink is the radio emission coming from these giant thousands of light years across jets coming out of the center of this galaxy. And when you look all the way down to the base of these jets, it goes right down to the center, to that supermassive black hole in the center. So that's also circumstantial evidence that says, well, the black hole doesn't actually affect the orbits, except very, very close to the black hole, of anything like gas and stars. But it's affecting something many, many thousands of light years and tens of thousands of light years away from the black hole with these jets. So this is a picture of Andromeda. I'm labeling the body parts. There's the disk of stars. There's a central bulge of stars. There's a halo that's a little bit harder to see, but stars are out there as well. So this is the stellar distribution of a typical spiral galaxy like our Milky Way. It also has interstellar gas that's full of dust. So you see the dust lanes in this particular galaxy picture. And the central black hole is located in the middle of the bulge. So where's most of the gas? Well, most of the gas that's associated with the galaxy is not inside where the stars are, but is surrounding the galaxy itself in this big, big gas cloud out there doing what I would say, a Gen X person like I is familiar with. It's slacking, right? It's not forming stars. It's just hanging out, waiting its turn. So most of the gas and the heavy elements that surround the galaxies is actually not between the stars or inside the stars. It's inside this, what we call circumgalactic gas. So if you look at a radio source like this, it's clearly interacting with something. And what it's interacting with is this big gas cloud around these galaxies. So we can directly study some of that gas, especially if it's in a massive galaxy or in a cluster of galaxies, using X-rays, because the gas is extremely hot. So this picture is showing you a picture that's assembled from 3 different telescopes. You see where the galaxies are, you see the central galaxy in the white, you see the radio in the blue, and you see the X-rays that are here coded as purple. So clearly X-rays are not purple. We can't see X-rays, but to visualize them, that's how we can do it. So where the purple is brighter, that's where the gas is denser. So one of my primary topics of study has been clusters of galaxies. Clusters of galaxies are where you can see all of this intergalactic gas emitting in the X-rays because it's so hot. And I've been very encouraged by the things that we can study in the X-rays around massive galaxies and clusters of galaxies, because what I can see is not only the radio, but I can also see how the hot gas is affected by the jets and the outbursts of the central supermassive black hole. So one of the most famous clusters of galaxies is known as Perseus. This is also a composite picture. The blue is showing you where the X-rays are. The red is showing you where the radio plasma is that's being ejected by the central object. The white is showing you where the stars are. And when I subtract off the smooth component of the X-ray image to show you where the wrinkles are, you see evidence for many outbursts, not just one outburst, but multiple episodes of the central black hole popping off, dumping energy into this gas, and then those bubbles rising like like a mushroom cloud arising from a nuclear explosion. I know that's an unfortunate image. I didn't mean to stress anybody out, but but it's the same sort of principle, that you dump some energy and that bubble rises and it expands when it moves out into gas that's lower density. So this is a simulation of that. What you're going to see is in the center of this orange stuff, which is the gas in the simulation, there is a rendition of a supermassive black hole dumping energy in the form of jets into an atmosphere that's much like the atmosphere around a massive galaxy. So I'll show that, and you see it turn on. And as it turns on, it generates instabilities in the gas that can cool, and that cold gas can fall back onto the black hole and provides the fuel for more activity. So it essentially can create its own rainstorm, and the rain from that storm is the fuel for more jet activity. So here it goes. Collecting cold gas, and then it can, so this is some pictures I took with the Hubble Space Telescope of in the ultraviolet that shows structures much like what this simulation from Yuan Li show in terms of the scale. So our own galaxy has had its own outburst. And this is a picture from the Fermi satellite, which is a gamma ray satellite. And this is, again, an all-sky picture on the right. That's the Fermi data, the gamma ray data. And it's color-coded so that the blue and the black spots are where there's very little gamma ray radiation. And then the white is where the Fermi telescope sees gamma rays. And you see two bubbles above and below the galactic disk. The disk runs right through the center. That dark band through the center of the all-sky image is our galactic plane. And so there's outbursts above and below this galactic plane. And over on the left-hand part of this diagram, you see an artist rendition of that, where it's all been made nice and smooth and symmetric by the artist. But you see the Milky Way disk running through the center, and then the purple gamma ray bubbles above and below. So I wanted to show you the data and the artist version of what might be going on side by side. So our own Milky Way supermassive black hole, right now fairly quiescent, apparently has had outbursts millions of years ago. So it's not always been quiet. So all this together seems to be assembling a picture or a story where central black holes are part of how galaxies regulate their own growth, right? So you have central black holes that can control how fast galaxies grow because it's regulating the state of matter, gas, well outside where the stars are, and it can limit how big the galaxies get, and it also can limit how big the black holes get. So central black holes don't hold the galaxy together. That's being grateful for dark matter. We don't want to be grateful to central black holes for something they're not doing. So just to be clear, it's the dark matter that's holding the galaxies together, but they act as these central sources of energy that can circulate heavy elements that the stars make. So this gas outside of these galaxies is highly enriched, but there's no stars out there sharing the elements. The stars are down here in the disks. So the supermassive black holes are actually pulling the gas that was formerly, in dead stars and distributing it and circulating it like a giant mixer to the surrounding gas. And then it's also dumping energy, and that energy can slow down the formation of future stars and keep it from running a little too hot. So if they weren't around, our galaxies would actually have even more stars and more vigorous recent star formation. And you're thinking, well, why should I be grateful for that? Because maybe if there are more stars, there'd be even more life or more activity. And I'll argue that maybe, now this is a lot more speculative right now, so, trust nothing I say at this point. But since you've been bearing with me so far, I'd like to put this out there. So if our galaxy had more star formation, there'd be more explosions close to us. And supernova explosions close to us might be bad, right? Because, not only might it, a very nearby supernova explosion might just, blow away the atmospheres of planets or something like that, but also could dump a lot of radioactive stuff onto, planets, or, just cause problems, in terms of excessive mutations or what have you. So more supernova might be more, say, gamma ray bursts or other things, and that could be hostile for life. Another thing that could be hostile for life, if you had a richness of stars everywhere, and maybe you had more life everywhere, more life might not be so great. So maybe if there were more aliens, life wouldn't be so good for us, right? Depending on how we were, had our relationships with the other aliens were. And given our relationships with each other, we don't need more. It might be cool, but we don't need more. I don't think we need more relationship challenges, at least not right now, okay? All right, so things to be grateful for: the Big Bang, the stars, the galaxies as birthplaces for those stars, the sun giving us free energy, and central black holes that circulate elements and regulate how much gas turns into stars and other black holes. So, my last slide is a slide that is actually a rendering from a VR thing that if you have one of those, VR goggles, you can actually go to this guy's website and look at what it would be like to fall into a supermassive black hole. But I'm just going to show you the rendering, the 2D rendering. But in VR you can look around. So if you got one of those goggles and all that, you should give this a go and let me know how it how it went. My son promised he was going to try it, but and he has all the things, but I don't. So I just have a lowly Mac. So here we go. Gravity around black holes is strong enough to bend light, and that's one of the things that's being stimulated here.
Say your prayers and so on. Don't forget, my son, to include everyone. I tucked you in, warm within, keep you free from sin, till the Sandman he comes. Sleep with one eye open, gripping your pillow tight. Exit light into night. Take my hand, off to never, never land. Something's wrong, shut the light. Heavy
This is a
thoughts
rapidly
tonight, and
spinning
they
black
are
hole.
so wide.
And what that means is the crystal space-time itself is dragged along and rotating around the black hole.
Sleep with one eye open,
And so
gripping
turning
your
to the left
pillow
here,
tight. Exit light into night. Take my hand, off to never, never land.
So thank you.